So what we're going to do is develop a velocity-based steering law. And I'm going to show you first what not to do. If we did a brute force, we could say, okay, I cannot independently come up with gamma dot and gamma double dot. That would be cool, but it just violates all kinds of laws. So we have to pick one. So I'm just going to say, okay, listen, this stuff, sorry, you're not on the left. You're not good enough. Bring it over, right-hand side. Then we're left with a system of equations where this becomes a 3 by 2n matrix, right? We have n devices, so this is an n by 1, and the total thing is 2n. And then each one of these d zeros and b's contains gs's and gg's. So it's a 3 by 2n matrix. That's a lot of, if you have 4 of them, that would be 8 columns in there. And we have to pick a wheel acceleration and a gimbal acceleration that will produce this right-hand side. That would be a brute force way of just solving for that. And you would do basically this 3 by 8 matrix for a 4 VSC system. You could do a minimum norm inverse again, like we discussed before. This would give you the smallest norm of angular accelerations that will produce this required torque. Why don't we do that? Well, the big reason is the thing we like about CMGs was the gyroscopic torques. That's what we want to take advantage of. And with this approach, you could solve for this, and then you could use motor torque equations to figure out, okay, this is the motor torque you have to apply and track that and do it, and that's cool. And that would work, but man, you're wasting a lot of money because you have a device that has this big momentum built in and you can gimbal it. That creates a huge torque, and you're basically going, I will just feedback compensate for all the money I just spent. You spend $1 million, I'm going to burn the $1 million as a first step, bring the stack down, and now I'm going to do something. That's essentially what you're doing if you do this. Your sponsor will not be very happy because they're expecting big performance, and you're going to get really meek performance if you do this out of that big device. And it will saturate like crazy, which means after it saturates, all your stability guarantees go out of the window that we had earlier, right? So don't be that person, right? Don't drive CMGs like a wheel. So instead, what we need to do is create a velocity loop. Now, if you've ever done these bicycle wheel experiments, you got a wheel spinning very fast, and you take it, it's really kind of surprising. You just tilt it a little bit and wow, I'm getting a really big torque. It doesn't take much. So the gimbal acceleration, so the gimbal rates we're talking about tend to be really slow, and to track a particular profile, we're talking about this earlier, these sine waves, we're going to try to get there, but we don't want to get there in a microsecond, because that would require huge accelerations. And that would now violate getting rid of this. We're going to redefine, so this is for the regulated problem, we had this. And we're going to show what to do here for the regulations case, but it's really a similar math. The classic CMG, what they would do is here, you got this part, the D0. The spinning inertia is always bigger than transverse for the wheels, but it's not hugely different, but it is bigger. And the big difference is omega 1 is much bigger than your wheel speed going at 10,000 RPM is so much bigger than your spacecraft speed about that axis. So while there are all these terms, as long as this wheel speed is big, then a classic CMG can make that assumption, right? Then you can just say, well, everything else I'm just going to ignore. And most papers that work on CMGs just ignore it up front. These are the equations, believe me. They don't tell you all the stuff they dropped to make that work. Their momentum will not be preserved if they were actually implemented in a physics-based simulation. But in the end, this is the control requirement of a classic CMG that we would have right now. Well, actually a variable speed CMG when I'm ignoring it. When we're doing D1, you could replace that with D1 minus D2 and get the D matrix we had earlier and include those terms. So that's a simple modification. And then you have something that doesn't require that wheel speed to be high to make that simplification. But the CMG people typically do, so that's why I wanted to show it once. So now we have to produce this. And you notice this has been dropped. There's no B anymore. So we're assuming in this control law that the gimbal accelerations times the gimbal inertia parts are negligible. That's a big assumption. So as long as it's acting as a full CMG, that works. But man, once you're going through zero, that's not exactly true. That's why zero crossing with VSCMGs, you won't track quite perfectly because you're losing some of the math with that stuff. You kind of have to get through it and then get to the other side. So we dropped that. But it also means, if you're looking at a servo loop, which you'll be developing too for the gimbals, you don't want to be too crazy. You want to track it well and track it quickly. But once you converge, you want to stay on top of it and there. If you have high accelerations at the beginning, because we're starting out with everything at rest, and then the control turns on and says, okay, you need to be rotating at 10 degrees per second with your gimbal. You can't go from 0 to 10 instantaneously, right? So, okay, so maybe you're a little bit aggressive and you go, wow, I got there. Now I'm moving at 10 degrees per second. And that caused accelerations that we kind of ignored. That might cause some unknown torques to act. But the key thing to remember is that disturbance is limited in time. It's only until you track your velocities. Once you're on top of the velocities, now you control how quickly those gimbal rates vary with time with your feedback gains. So don't try to do something that is going to be switching back and forth and have super fast accelerations, very high frequency stuff, because that's going to have huge accelerations again. Typically, we're still doing, spacecraft, rotating. Maybe it's a big space station or something that has to rotate a little bit faster, so I need bigger torques. But it's still a very smooth motion. The rotations aren't doing this. The rotation is fast, but you can be fast with a low acceleration, right? You just you accelerate more and more, and then you coast, and then you decelerate at a constant rate, and you go down. And that's easy to do with these systems. So that balance, when you do feedback gains, this will be a challenge. It's not a huge challenge, but it's something you need to be aware of when you're doing your tracking controls. And you put in a reference that's just really wild with 100 hertz. There are assumptions in there that all of a sudden are going to come back and bite you, because your simulation is going to do the full thing with gamma double dot. That's what you're simulating. Make sense?